we were faced last time with the question of interpretation of the Schrödinger wave function. And so to recap of the main ideas that we were looking at, we derived this Schrödinger equation, basically derived it from simple ideas having operators, energy operator, momentum operator, and exploring how the de Broglie wavelength associated to a particle would be a wave that would solve the equation. And the equation was the Schrödinger equation, a free Schrödinger equation. And then we added a potential to make it interacting. And that way, we motivated the Schrödinger equation. And it took this form of x and t, psi of x and t. And this is the dynamical equation that governs the wave function. But the interpretation that we had for the wave function, we discussed what Born said, was that it's related to probabilities, and psi squared multiplied by a little dx would give you the probability to find the particle in that little dx at some particular time. So psi of x and t squared dx would be the probability to find the particle at that interval dx around x. And if you're describing the physics of your Schrödinger equation is that of a single particle, which is the case here, one coordinate, the coordinate of the particle, this integral, if you integrate this all over space, must be 1 for the probability to make sense. So the total probability of finding the particle must be 1, must be somewhere. If it's in one part or another part or another part, there's probabilities. For this to be a probability distribution, it has to be well normalized, which means 1. And we said that this equation was interesting but somewhat worrisome, because if the normalization of the wave function satisfies, if this holds for t equal t naught, then the Schrödinger equation, if you know the wave function all over space for t equal t naught, which is what you would need to know in order to check that this is working at time equal t naught, you take the psi of x and t naught, integrate it. But if you know psi of x and t naught for all x, then the Schrödinger equation tells you what the wave function is at a later time, because it gives you the time derivative of the wave function in terms of data about the wave function all over space. So automatically, the Schrödinger equation must make it true that this will hold at later times. You cannot force the wave function to satisfy this at all times. You can force it maybe to satisfy it at one time, but once it satisfies it at this time, then it will evolve, and it better be that at every time later, it still satisfies this equation. So this is a very important constraint. So we'll basically develop this throughout the lecture today. We're going to make a big point of this, trying to explain why the conditions that we're going to impose on the wave function are necessary, what it teaches you about the Hamiltonian. Will teach you that it's a Hermitian operator, what do you learn about probability? You will learn that there's a probability current, and all kinds of things will come out of taking seriously the interpretation of it as probability. The main point being that we can be sure it behaves as a probability at one time, but then for later times to behave as a probability, the Schrödinger equation must help, must somehow be part of the reason this works out. So that's what we're going to try to do. Now, when we write an equation like this, and more explicitly, this means integral of psi star of x and t, psi of x and t dx equal 1, you can imagine that not all kind of wave functions will satisfy it. In particular, any wave function, for example, that at infinity approaches a constant will never satisfy this. Because if at infinity you approach a constant, then the integral is going to be infinite. And it's just not going to work out. So you cannot, the wave function cannot approach a finite number, a finite constant as x goes to infinity. So in order for this to hold, order to guarantee this can even hold, can conceivably hold, will require a bit of boundary conditions, and we'll say that the limit as x goes to infinity, or minus infinity, plus minus infinity of psi of x and t will be equal to 0. It better be true. And we'll ask a little more. Now, you could say, look, certainly the limit of this function could not be a number, because if it would be a non-zero number, the integral would diverge. But maybe there's no limit. The wave function is so crazy that it can be integrated, but suddenly it has a little spike, and it just doesn't have a normal limit. That could conceivably be the case. Nevertheless, it doesn't seem to happen in any example that is of relevance. So we will assume that the situations are not that crazy that this happens. So we'll take wave functions that necessarily go to 0 at infinity. And that certainly is good. You cannot prove it's a necessary condition, but if it holds, it simplifies many, many things. And essentially, if the wave function is good enough to have a limit, then the limit must be 0. The other thing that we will want is that the psi dx, the limit as x goes to plus minus infinity, is bounded. That is, yes, the limit may exist and it may be a number, but it's not infinite. And in every example that I know, in fact, when this goes to 0, this goes to 0 as well. But this is basically all you will ever need in order to make sense of the wave functions and their integrals that we're going to be doing. Now, you shouldn't be too surprised that you need to say something about this wave function in the analysis that will follow, because the derivative, you have the wave function and its derivative, because certainly there are two derivatives here. So it's when we manipulate these quantities inside an integral, as you will see very soon, single derivatives will show up, and we will have to control them. So the only thing that I'm saying is that when you see a wave function that satisfies this property, you know that unless the function is extremely crazy, it's a function that goes to 0 at plus minus infinity. And its derivative presumably also goes to 0, but it will be enough to say that it maybe goes to a number. Now, there's another possibility, I think, for confusion here with things that we've been saying before. We've said before that the physics of a wave function is not altered by multiplying the wave function by a number. We said that psi added to psi is the same state. Psi is the same state as square root of 2 psi. All this is the same physics. But here it looks a little surprising, if you wish, because if I have a psi and I got this already working out, if I multiply psi by square root of 2, it will not hold. So there seems to be a little, maybe something with the words that we've been using is not exactly right. And I want to make sure there's no room for confusion here. And it's the following fact. Here, this wave function has been normalized. So there's two kinds of wave functions that you can have. Wave functions that can be normalized and wave functions that cannot be normalized. Suppose somebody comes to you and gives you a psi of x and t. Or let's assume he gives you a psi. I'll put x and t. No problem. Now, suppose you go and start doing this integral. Integral of psi squared dx. And then you find that it's not equal to 1, but is equal to some value n, which is different from 1, maybe. If this happens, we say that psi is normalizable. Which means it can be normalized. Using this idea that changing the value, the coefficient of the function, doesn't change it too much, we simply say, use instead that a psi prime, which is equal to psi over square root of n. And look what a nice property this psi prime has. If you integrate psi prime squared, it would be equal, because you have psi prime here squared, it would be equal to the integral of psi squared divided by the number n, because it's two of them, dx, and that's the number goes out, and you have the integral of psi squared dx, but that integral was exactly n, so that's 1. So if your wave function has a finite integral in this sense, a number that is less than infinity, then psi can be normalized. And if you're going to work with probabilities, you should use instead this wave function, which is the original wave function divided by a number. So the idea is that in some sense, you can delay all of this, and you can always work with wave functions that are normalizable, but only when you're going to calculate your probabilities. You can take the trouble to actually normalize them, and those are the ones you use in these formulas. So the idea remains that we work flexibly with wave functions and multiply them by numbers, and nothing changes as long as you realize that you cannot change the fact that the wave function is normalizable by multiplying it by any finite number. It will still be normalizable. And if it's normalizable, it's equivalent to a normalized wave function. So those two words sound very similar, but they're a little different. One is normalizable, which means it has integral of psi squared finite, and normalized is one that already has been adjusted to do this and can be used to define a probability distribution. Okay, so that's in a way of introduction to the problem that we have to do. Our serious problem is indeed justifying that the time evolution doesn't mess up the normalization. And how does it do that?